Hello everybody, my name is Mattia Fumagalli from the Conceptual and Cognitive Modeling Research Group at University of Bolzano. This work was titled is Pattern Discovering Conceptual Models Using Frequent Itemset Mining, is the output of the fruitful collaboration with Tiago Prinsales and Giancarlo Guizzardi. The main goal of this work is to propose a highly automated and interactive approach for the discovery of patterns from conceptual model catalogs. Here, of course, we are concerned with patterns in conceptual modeling. Typically, in this context, patterns emerge from the repeated modeling practice in a given field. These recurring structures are used by the modeling community for a range of different purposes, including to understand how languages are used in practice. The popularity of patterns in conceptual modeling is demonstrated, in particular, by the growing number of pattern catalogs. At the current state, our proposal is mainly concerned with a specific type of modeling patterns, namely structural modeling patterns. These modeling fragments represent recurrent structures formed by modeling constructs of a given conceptual modeling language. Figure 1 shows examples of very common usages of the generalization relationship in UML class diagrams. Figure 2 represents 3 examples of recurring structures in BPMN. These patterns correspond to equivalent ways of modeling tasks parallel splitting, and are related to how people design control flows. Pattern discovery, however, if performed manually, is a highly laborious and challenging task. This is the reason of why it usually takes years for pattern catalogs to emerge. We can highlight 2 main reasons of such a difficulty. First, the sheer size of data to be analyzed. Second, searching for patterns consists of difficult steps for humans, such as partitioning models into smaller fragments, calculating the frequency of candidate patterns, and filtering out constructs of interest. For instance, when one is looking for taxonomic structures in domain models. Given this situation, there is a common agreement that the field will highly benefit from the creation of automated data-driven techniques for the empirical discovery of structural patterns. Still, the automation of these tasks remains very challenging. Why the automation of pattern discovery is so challenging? Here are some possible reasons. For instance, the approach should be able to discover interesting patterns. The approach should support the manipulation of input models so that the user can look for a particular type of pattern. Again, the approach should support the assessment and analysis of the output patterns by generating human-readable visualizations and providing statistical insights. The approach should be accurate enough. The approach should work with any conceptual modeling language. What about the current state of the art in automatic approaches to pattern mining? We can say that current graph mining approaches can be very helpful, but present multiple issues, especially for what concern. First, the complex semantic information inside conceptual models. See, for instance, in UML, cardinalities, class labels, property labels, generalizations, generalization sets. Second, the customization of the process, which is very complex. See, for instance, partitioning, filtering, and so on. Given this scenario, we propose here an approach that focuses on the customization of the process and the complex semantic information inside conceptual models. The whole approach is then composed by the following tasks. The first one is filtering, where the user can select what language constructs to filter out from the models. For instance, in the case of UML, one may want to look for patterns only involving classes decorated with certain stereotypes, or involving only classes, generalizations, and generalization sets. The second task is abstraction, which allows the user to input a set of transformation functions to be applied to the models, by which certain constructs can be abstracted into more general constructs. For instance, in Archimate, business processes, business functions, and business collaborations may be abstracted into business internal behavior elements. This step allows users to look for more general patterns that apply to several types of constructs. The next task is importing, which consists of taking a set of conceptual models encoded in a given language and transforming each model into a graph. Notice that this is not always an obvious task. Consider, for instance, the transformation of UML class diagrams into graphs. The simple solution is transforming classes into nodes and generalization and associations into edges. Still, if we want to convert generalization sets, association classes, generalizations between associations, cardinalities, and several other constructs, that no longer works. This task is language dependent and requires an ad hoc transformation for each source conceptual modeling language. The following task is discretization, which takes each graph, namely the output of the importing task, and splits it into graph partitions that represent subset of the input conceptual model. We do this by a repeated execution of the Kernighan-Lin bisection algorithm, which splits a graph into two balanced bisections until we obtain graph partitions with at most n nodes, where n is the threshold value provided by the user. Through the next task, namely normalization, the graph partitions are relabeled and indexed to enable the detection of patterns across them. The relabeling of the graph partitions occurs by firstly associating both a label and an index to each node, where originally the node corresponds to an ID, and the label corresponds to the language construct associated with that node. The next task, namely the embedding task, converts normalized graph partitions into item sets. Here, each graph edge is transformed into an item. This enables to mine all the information encoded by the node and the edges labels. Notice also that this allows accounting for the rich amount of information encoded by conceptual models. For instance, an item can easily represent nodes and edges labels, properties with their source and target cardinalities, and related directionality. The mining task represents the final part of the workflow, and is aimed at generating the candidate patterns and making the output accessible to the user for the final assessment. This task allows for another interaction with the user, who can select the frequency threshold for the output patterns or some ad hoc parameters of the mining algorithm. The output of the mining task will then consist of a list of discovered patterns in a format that eases the final assessment, and a set of frequency measures for each output pattern. These frequency measures are the absolute frequency, calculated as the number of pattern occurrences over the total number of item sets generated through embedding, and the model frequency, calculated as the number of pattern occurrences over the number of conceptual models used as inputs of the whole process. For instance, given 5 models, we can have a pattern occurring with an absolute frequency of 10, but the model frequency cannot be more than 5. To validate the approach, we firstly implemented an interactive command line application, which is freely available. We tested the approach over around 120 models represented through the OntoUML language, which is a pattern-based well-founded extension of UML class diagrams. The main goal of the experiment for the validation was to find 6 well-known patterns and check how the tool performs with regard to a set of requirements gathered through an interview of 5 expert language engineers. Here's some quantitative information about the results of our experiment. Each chart shows the data for a pattern. Bars represent found occurrences number. The 6 charts on the left refer to absolute frequency data, while the 6 on the right refer to model frequency data. The red line in each chart is the total number of occurrences manually found by the user. The blue and purple lines represent the Jacquard index for the absolute frequency and the model frequency. One first observation is that the approach is able to find the patterns we selected beforehand, which are clearly mapped into the output pattern graphs. Secondly, it can be noticed that the partition parameters have an impact on the reliability of the process. This seems to be dependent on the structure of the pattern. Moreover, in the trials where the user interacts with the application to filter out information, the reliability improves in most of the cases, thus demonstrating the key role of the customization features implemented in our approach. Finally, for what concerns the reliability overall, the current implementation is clearly better in calculating the model frequency. For more details about the validation data, please check the evaluation section in our paper. Here, to give an example, we have an output pattern, namely the subkind pattern, found in the experiment trial, with the absolute frequency and the model frequency reported. The graph, along with the values, is one of the outputs of the application. Here, another example of a more complex subkind pattern found in one of the trials. In this case, the absolute and model frequencies are lower because of the complexity of the pattern. Here, an example of roll mixing pattern. Finally, here, an example of a known pattern, which shows a higher level of complexity with both generalization and associations. In this link, you can find the proposed application and all the outputs of the experiment with other example patterns. As a conclusion, based on the results from our evaluation with the dataset of OntoUML models, we envision a series of next steps. First, we will test in collaboration with language designers if our approach can find unexpected patterns in OntoUML. Second, we are going to improve the accuracy of the results by evolving the embedding and the mining steps. Third, we will test our approach with models encoded in different modeling languages, such as BPMN and Archimedes. Thank you for your attention. If anyone has any questions, I will be happy to open up the discussion. And if you would like more information, please check our paper and related repository, or feel free to contact us via email.